Hi, everyone. So I'm going to begin. It's a little after 3 p.m. This will be covering just a little bit of a differential equations review that I've gone over, and these are going to be some definitions that'll really help you out for circuits 1 and just in general for differential equations. This will definitely come in handy in future classes and anything to do with ordinary differential equations. This first document right here, we'll go over the definitions such as independent, dependent variables, linearity, homogeneity, and order, describing the relationships between them and distinguishing the best ways that you can go about solving for these ordinary differential equations. This is being done for a circuits class, so we'll pay strong attention to linearity, especially because in your first year circuits courses, linearity and things being linear is going to be something very important to assist you when you're just working with linear elements rather than elements such as diodes, transistors. So we'll begin here on independent versus dependent variables. These are really important to distinguish when you begin your differential equations. So an independent variable is going to be a variable that acts independently, hence the name independent, from others. Now, these are going to be variables basically that are unaffected by other things, other variables within the equation that we're looking at. Now, conversely, the dependent variable is going to be, you could probably guess it, they're going to be dependent on other variables. And now these are going to be they're going to be directly affected by other variables. Now, exactly what this means is something that we need to look into, right? Because when we're deriving something or when we're going through a differential equation solution, exponential, and whatnot, knowing what your independent variable is and what your dependent variable is will be crucial in understanding that function altogether, what you're deriving with respect to, what your output, what your input is, especially because when you have your output, input, we're taking something in, right? Let's say X and Y, and we're going to get a function out, right? So we need to pay attention to what our independent and what our dependent is going to look like. So now we can look at some examples of this here. Now we can start and look at the first one. So really we have two columns here for independent and dependent. And what we're doing is this isn't something where you distinguish and say, oh, this equation is independent. No, you're choosing the variables in this equation that are independent and then choose the variables that are dependent. So for this equation, and we can do the first one or two. Beginning with, you'll have your independent variables from here and your dependent variables as well. So looking at it, we can see we have our function, and going back up here, we see we have our inputs and then the output function. Coming back here, we can see we have f of x, y, z relative to a. So what's inside here are the variables that are independent from the others. They're going to be the ones that are not directly affected. And those are going to be our independent variables. So we'll have our independent is going to be x, y, and z. And then our dependent from here can just be a. Now following that, we can go to our next one. And these next three are similar when we look at like dy over dx. And the best way to think about this is what we are deriving with respect to. So that's usually what I think of it when I'm thinking of between independent and dependent, is what am I deriving with respect to? So if we had dy over dt, which is usually used for time, you're deriving with respect to t. T is being your time. And that means that your independent variable is going to be what's on the denominator. So dy over dx is going to have your independent as x and your dependent being y. Moving on to that, we can do the same exact thing when we're going to the next equation we have here. Is we can do exactly what we did. We can look at the independent or the denominators and the dependent, which will be the numerator here. So it's pretty easy to pick out. You could see it. It'll be, our independent will be u and w. So u. And our dependent will be capital V. Now this last one, and I put this equation coming up multiple times in this review, we'll come back to it many times, is because this looks like something you'll see on, especially with circuits. So we have our VC of t, C usually denoting a capacitor. And this follows the same exact thing. As I was saying, you have your dt on the bottom, right? We're deriving with respect to time, and then the VC of t. And that comes back to here, right? We had f of xyz. Xyz was our independent. So we have VC of t, right? So in both cases, t is our independent. And we can see that for our second one as well. So our independent on this one's going to be t. And our dependent is going to be what's on the top here, and that's just going to be VC, right? The VC will be up here. Then we have also our function here, right? VC of t, which would be similar to up here. We have f of xyz. So also in this one, we could say dependent is f. But I put a, because a is at the beginning and describing the whole function. So the dependent here would just be v sub c. So, any questions? Yeah. Awesome. So the next thing, and this will be the next kind of definition, we move on to linearity. And now I also said this is really important with circuits, or the beginning of circuits, is knowing whether something's going to be linear or not. In our case, and what we're mostly studying here, we're going to be dealing with linearity a lot because we haven't really gotten into other elements that move away from linearity. As we were talking today, especially with like an inductor, it was just a straight linear line that was the slope of the inductance, especially in frequency response. So linearity is just going to be the dependent, it matters with the dependent variable and its derivative occur directly. And now, what does that mean? Basically, what that means is the dependent variable and its derivatives are to the first power. So if we had a dependent variable being y, that means y will only be y to the power of 1. We're not going to see y squared. We're not going to see y cubed, anything higher, because that'll break linearity. So we can go to the examples. The examples will funnel exactly what I said. So we look, and now you gotta be careful because you can't just look and see that it's you see the 3 here, the cubed. That doesn't necessarily mean the dependent variable is to the power of 3. That means the third derivative, right? And that'll be the same here. So our dependent variable in this case is, going back to what we did, is you can take a second and think, it's going to be y, right? So x in this case is the independent, y is the dependent. So the only part we really got to look at is this 5x cubed. And now that is not linear, but in this case it doesn't matter because x is our independent variable. So in this case, this would be linear. And we can look at the next one. And we have the second derivative plus e to the x, first derivative plus e to the y. Now, is this linear? The first thing I would do, especially in all of these in determining linearity, is determine your dependent variable. So in this case, our dependent variable is y. And now we can check this term. Is it y linear? Awesome. E to the x, that doesn't matter because that's our independent variable. And now the last one, would e to the power of y make this nonlinear? You think so? No. This would break linearity. It would be because if you think of it, it would basically make it exponential rather than so polynomial exponential, just kind of going up the list of it. So this actually would be nonlinear, which is a good example to look at because at first glance you wouldn't think so either. Yeah. No, I assume you're recording. Mm-hmm. Yeah. So we can move to the next one. We have our independent x and our dependent y. This one's pretty easy to spot out. Is this whole thing, the whole first derivative is to the 5th power. So immediately we can see that this is not going to be linear. And now lastly, we get back to that first, the last of the first part is this is an equation you'll see a lot when you're working with circuits, or just the general form, right? R you can take as a resistance, C you can take as a capacitance. And then the VC of T, or VC, is going to be our dependent variable. And we can look, and that's good. That one's good. And then this one doesn't even have VT in it. So this one would be linear. And now this is something, this equation here, this last one, is good to understand and good to see, because this will definitely be something you'll come into contact with when dealing with circuits, and especially first order transients and further on. So can get to the next definition. There's only about 2 more, and this one's order. I would say order is very closely related to linearity, and it's kind of looking for the same exact thing, but now you're classifying it. So order is just the value of the highest derivative in that equation. So now, rather than linearity, where you're looking to see if there was a like higher power, now you're looking at the derivatives, and you just want to see where's the furthest derivative down we're going. Like how far into derivatives are we? And this one is pretty easy to jump out to you, because if we changed it to, say, this one, so we have the third derivative here and second derivative. If this were switched to, say, y triple prime, that would be the same thing, y prime prime prime. So putting in this form, we can see that it's 3, that's 2. Now, it could be, usually they're written in order, but you could have a fifth derivative on the right side. That's why it's good to look at all of them. So this one's pretty easy to figure out, and this would just be third order, because our highest derivative in this equation is 3, third derivative. And now what I meant by the y triple prime is this could also be written as y prime prime prime. Once you pass 3, keep in mind it could be written as y parentheses 4. Now, if it's in the parentheses like that, it means fourth derivative. If it's not, then it would be to the fourth power. So that's something you need to look for. But usually, if it's going that high, you'll see it in this form. Now, the second one, pretty easy to figure out as well. There's not much of a change there. That one would just be second order. Now, third one is same idea. You need to watch out for the 5 to the fifth power. Now, that doesn't change it. So this is the first derivative to the fifth power. That does not mean the fifth derivative. Those are two different definitions. So this would actually just be second order. And now the last one is back to that same equation. Is you want to find we got what? The first derivative, no derivative, and then a constant is on the end, right? We can see that VOC is different than VC of t. VOC would usually be the initial condition. That would be the beginning. So the right side is actually going to be our constant. So this one would actually go down even one more. So our highest derivative is 1. So actually, this one is just the first power, the first order. So I think order is one of the easier ones to figure out. And then we move on to the next one. Really looking at it, we got independent, dependent, linearity, order, and homogeneity. I would say that linearity and homogeneity might be the two hardest to pick out. Linearity becomes easier over time. Like you'll start seeing, especially when you graph something. You know, if you really don't know, put it in a calculator and see if it's a straight line. If it's not a straight line, then it's not linear. Homogeneity, this one is a little different, but still pretty easy to figure out. And this one's still a lot of things, and you'll notice is in this, this comes back to the definition of a dependent variable, is dependent on other variables, right? That's kind of a given definition. And then linearity depends on the dependent variable, right? Homogeneity also depends on the dependent variable. So all terms in the equation, to be homogeneous, all terms in the equation must contain the dependent variable. So all terms must contain dependent variable. And now, just like this one, and just like linearity, the first thing I would do is figure out your dependent variable, right? If you need to know it must contain the dependent, you should know what the dependent is. So looking at the first one, we can see that the independent is going to be x, and then the dependent is going to be y. So the first one contains the dependent variable, right? It contains x. And the, sorry, my bad. The dependent is y. The independent is x, my bad. So the first one contains the dependent variable. Does the 5? No, right? So this would be non-homogeneous, exactly. So we can look at the next one, and we can find our dependent, independent. Our dependent is going to be the y. So this one contains it, right? Because we have the second derivative, the y is there. One little like misconception I first had when I was first doing differential equations, figuring these out, is I saw the dependent variable as y, but I thought it had to be somewhere out here too. It doesn't. It's right there. That's good enough. So the next one also has dy over dx, with it has our dependent, and the last one does. So all three terms in the equation have the dependent variable y in it. Therefore, this one is homogeneous. And lastly, we have a little different form of that same equation we've been looking at up here. And this one has our dependent VC, and it's also over here too. So this one would also be homogeneous. And keep in mind, this is only on the left side of the equation, right? So this is an equation because we have it set equal to 0. It only needs to be on the left side. It doesn't need.
That was equal. What if that was equal to, like, you know, whatever dc of t on the right side though?
Mm-hmm.
That would.
Yeah.
The right side of the equation just doesn't matter.
It wouldn't matter in this case.
At all. So if it didn't have dc, or if it did, it'd still be homogeneous.
Yeah. Exactly. Because if you moved it over, it would be exactly. Awesome. Yeah. Oh, and then I did include the full last equation. So now we look at what we did here, and right, it's in both of them. So this is now the same equation, kinda, but we have this end part. So the VC of t, the VC is still our dependent. So it's in the first one, in the second. Is it in the third? No, it's not in the third. So this would be non. Yep, exactly. So, and it's easy to see you see the VC, then you see the VOC. They're not the same. So that it would be non-homogeneous. And now we come to two different definitions, and these are going to be very important definitions when you're solving for the equations. And these have come up a few times now. And the best way I've seen it and explain it is by the example I'll get to, but I'll go to the general definitions first. So the forced solution is going to be basically going to be the system's response to an external stimulus. And external stimulus is basically just going to be some external event, something else that happens. But an important thing here would basically going to be it has no initial conditions. That's one of the important parts of the forced solution. So it's going to you'll see that it's like K1 e to the st. know the initial conditions. And this is usually referred to as inhomogeneous or the particular solution. And now the natural solution is it's just the opposite of this. So it's going to be the system's response to what we now have our initial conditions. And there's going to be with no external force. And this is going to be your homogeneous, or another word is complementary. So that's a little seeing it, if you're seeing it for a first time or again or anything, it's a little daunting to just see those two definitions. The best way I've seen it is the example, and this is I was thinking through examples. I thought this was a really good one. So if you've ever seen like a memory foam pillow and you like push into it and it sticks, it like stays in there. So you could think of the two different things. So your force solution, your particular force response is going to be you with the external stimulus pushing your hands into the pillow. That's the force response. The force response is the pillow sinking in because you pushed on it. And the natural response is going to be what happens because of your initial conditions. So your force response is pushing into the pillow. The natural response is it slowly inflating back up, right? The initial conditions is you pushed on it, and then it inflates back up. So the force will be pushing into the pillow. The natural response, the complementary, will be what happens after. So the pillow coming back up. And then this leads to just some fill in the blanks. And these contain some pretty important relationships to know. So the first one is something we've already used a lot in. So the answer is almost always to use a blank kind of function as the homogeneous trial solution. This is what we've used in class and what's done a lot. It was even one of the answers to one of the beginning examples. It's an exponential function. Yeah, right. You're thinking that. Yeah. And when you're talking through this, when you're going through differential equations, that's usually it's like the guessing zero on any test. If you don't know the answer, that zero is probably a pretty good choice. Exponential is usually what's going to be used, and I mean that's exactly what it's saying here. The answer is almost always an exponential function. And we'll see that, right? We have like e to the st. That's exponential, right? E to the st. We have our k1 e to the st. It doesn't have to be k1 is just an arbitrary constant, which we'll also get to. Actually, that's the next one. The homogeneous solution always contains arbitrary constants. It's always going to have arbitrary constants. And the arbitrary, right? The constants could be anything. So if you don't see a constant in front of it, it has one. It's just one.
And those are like the a before the e to the st or whatever.
That's the arbitrary constant, exactly. Yeah. So if you'll see a e to the st when you're solving them. A is the arbitrary constant. If you're doing like a second order, you're just doing something further, you'll have more than one. Right, you have two. Say you have an inductor and a capacitor, you're going to have two arbitrary constants. The next one continues on from this, so I'll fill in the first one. So the amount of arbitrary constants is going to be equal to the blank of the equation. This is one of the 4 things we did before. Order, exactly, yep. The amount of arbitrary constants is equal to the order of the equation. So consider a second order transient, right? Second order. Then I was just kind of going over that. You have 2 arbitrary constants, second order.
Now, for that, it's a second order because we would have an inductor and a capacitor.
Or we would have 2 reactive elements. So you could have 2 inductors, 2 capacitors. Exactly, yep. And you could go further, but that exponentially makes the work go up. So
you had like 3 inductors or something, you have a third order,
but you'd have to do a lot more, yep, exactly. And then we have the most important property of a differential equation depends on its, this is also something, it's another reason why we're dealing with only these types of equations, is because once you get past these, once you get into like diodes or transistors, they break linearity. So it'll go down in a parabola, or it'll change on a nonlinear curve. So the most important property of a differential equation depends on its linearity. So that's something you'll be really happy with, is when you're dealing with the differential equations. If you're going through it and you see that it's linear, that'll put a smile on your face. Because once you get past that, quiescent points and further, it becomes a lot more difficult. And just the reason we first got into calculus, right, and sine waves and other things, when things get nonlinear, it adds a lot more math. And then the last one, the number of required initial conditions also equals the blank of the equation. That's also going to equal the order, right? Yeah. So, and that goes back to the arbitrary constants. So, number of required initial conditions equals the order of the equation. So, last thing I can add here at the end is, let's talk about trial solutions real quick. So we kind of already went there at the beginning. Answer is almost always an exponential function as a homogeneous trial solution. So just explaining trial solutions, what are they for? I'll just do what for. They're going to be for linear. You're going to look for these. You want to see if it's linear, homogeneous, with constant coefficients. Lucky enough, in the course here, circuits 1, that's what we're dealing with. So that's why our trial solutions, exponential trial solutions, that's why they work, is because that's all we're dealing with. And basically, what's their purpose? And this is helping us solve it, is they reduce it to a characteristic polynomial equation. And you'll see that as like AS squared plus BS plus C. Remember, you don't want that A. You're going to have to divide that A out. We want the coefficient of the highest to the highest order. We want it to be 1. So if you did see AS squared plus BS plus C, you want to do S squared plus B over AS plus C over A. Because we don't want any we want the coefficient in front of the highest order to be 1. And I think I have one more thing about trial solutions on here. Oh yeah, and basically the last thing is the trial solutions, the constants that are The constants that are found in the trial solutions are from the initial conditions. The initial conditions is going to give us the initial conditions are going to help solve it. Or it's going to help solve it because it's going to allow us to find the constants, the constants A, B, and C here. So, do you have any questions?
Not yet.
No? Awesome. That's it for this. So I'll stop this.